Okay, and this is the 2020 AMC 10B, problem number 11. Miss Carr asks her students to read any of the 5 of the 10 books on a reading list. Harold randomly selects 5 books from the list and Betty does the same. What is the probability that there are exactly 2 books that they both select? Okay, we're going to use a little bit of a tactic here to save just a little bit of time. Obviously, me explaining it slows it down, but if I wasn't explaining, think of it, what if they both rolled dice, right, instead? What is the chance they get matching numbers? You could list it all out, 1, 1, 1, 2, all the way to 6, 6, right? And there would be 1, 1, 2, 2, 3, 3. There would be 6 out of 36 if you did that. But a different way of thinking about it is if Harold gets the number 2, what's the chance that Betty gets the same number? She'll have a 1 in 6 chance. And if he had a 3, a 1 in 6 chance. And no matter what he gets, she has a 1 in 6 chance. We're going to use that same kind of thinking on this problem. It doesn't matter what books Harold selects. We can just go from Betty, and whatever books Harold has, she's going to select 2 of them. 2 of Harold's books, and 3 that are not part of Harold's books. Because Harold has 5 books, she has 2 of those to choose, and the 5 books Harold doesn't have, she's going to choose 3 out of 10 choose 5. It's because Harold's books are arbitrary. Just like in the dice problem, whatever Harold got was arbitrary. He could have gotten anything, she will have a 1 in 6 chance of matching. This is the answer, we just need to calculate. You should remember 5 choose 2. It comes up so often. This is 10 times 10. 5 choose 2 and 5 choose 3 being equal. Over 10 times 9 times 8 times 7 times 6 times 5 factorial. Over 5 factorial, 5, 4, 3, 2. And the 5 factorials cancel. I don't usually write the 1. The 3 and the 2 can make into 6. The 10 can go into 20 and leave 2. The 2 can go into 8 and leave 4. And we're going to have 9 times 4 times 7 left over. You got them right here. So that's, I don't know, 63 times 4. Actually, we don't need to do that. There's 2 2's in the 4. So put 1 2 in here and 1 2 in here to get 5. 5 times 5 is 25 over 63. That's the answer. It's D. All right, and this is the 2020 10B problem number 12. The decimal representation of 1 over 20 to the 20th consists of a string of zeros after the decimal point, followed by a 9 and then several more digits. How many zeros are in the initial string of zeros after the decimal point? You got to think about a way of attacking this. The first thing I think about is take the 20 to the outside. So it's 1 over 20 to the 20th. Then I want to think, there's a few options. You could make this like 5 over 100 for some reason. But I think what I want to do is split it into 1/2 to the 20th times 1/10 to the 20th. And this is because a times b to the power of x is equal to a to the x times b to the x. And so we can just split this into 2. Now this becomes 10 to the negative 1 to the 20th power, which is 10 to the negative 20. If we could just find what this looks like, or how many zeros it creates after the decimal point, we could then move it 20 more to the left, and we would get the number of zeros, because every movement to the left will create another 0. Okay, so let's go with that plan of attack. There's probably, by the way, a logarithm way of doing this. I tried to think of a different way during it and wasn't able to. So what we're going to do now is make this basically, let's do 2 to the 10th is 1,024, and 2 to the 10th squared is 2 to the 20th. So if we simply square 1,024, we will get 2 to the 20th. And to save some time, it comes out 104,8576. Okay, So once I have this number, 104,857,6, 1,048,576, it's in the denominator of this. So 1 over 104,857,6. How are we going to find out how many zeros that generates? Let's think about 1 over any number. What if I had 1 over like 128, which is 2 to the 7th? Okay, then you would do 128 goes into 1. It would go in 0 times, and you'd put a decimal point and add a 0. It's still not going to go in, so you'd put a 0 and drop another 0. It's still not going to go in, so you put a 0 and drop another 0, and now it's going to go in. You'll notice the total number of zeros at the top, including the one to the left, is equal to the number of digits. So I wonder if that's always true. We could check with like 1 over 64, which is 2 to the 6th, and 64 goes into 1 0 times, drop a 0, still goes in 0 times, and now it's going to go in. So we get 2 zeros here, which is the number of digits, and you get 2 zeros up here, which is also the number of digits. So we have 3, 6, 7 digits here. That means we're going to get 1 0 on the left, 6 on the right. It's going to say 0.12345 and then 9 whatever, right? And now all we know it's 9 because of up there. Then 10 to the negative 20th is just going to shift this 20 times this way, adding 20 more zeros. So these 6 zeros and those 20 zeros give 26. All right, now for the 10B from the 2020 test, problem number 13. Andy the ant lives on a coordinate plane and is currently at negative 20, 20, facing east. Okay, so for the directionally disinclined, that is in the positive x direction. Let's just put a point here. We'll call this A sub 0 where he starts, and he's facing this way. So he's going to go, it says Andy moves 1 unit, so this is right here. He's going to then turn left 90 degrees. From there, Andy moves 2 units north, so now we go 2 units, this is 1 unit, and then turns 90 degrees left, which is again this way. He then moves 3 units, and then west, and again turns 90 degrees left. And then Andy continues this process, increasing his distance each time by 1 unit. So he went 3 here, he's going to go 4 here. And always turning left. What is the location of the point at which Andy makes the 20/20th left turn? Now, it might seem like it's going to take a long time, but we just look for a pattern and then capitalize on the pattern. Just try a few out. So you put A sub 0 here to represent he doesn't make a left turn from that position. From this position, he makes his first left turn. So we know that A sub 0 is negative 20, 20. We know that A sub 1, if you're going 1 this way, the x value is going to decrease, the y value stays the same, or whether it's increased, sorry. A sub 2, you went up 2, so your y value is going to go up 2, your x value will stay the same. A sub 3, which is over here, is going to be, you lose 3 to the left. So you're going to go back to negative 22, positive 22. And then on A sub 4, you are going to go down 4. So you will be at negative 22 for the x value. Down 4 will put you at 18. Now, let's think about what's going on here. From the beginning, he's now going to be going this way again, right? So traveling the same way he was when he went from A0 to A1. So let's see what happens when he goes there. If we add 5 to this, A sub 5, because this is A sub 4, this is A sub 5, adding 5 to this will be negative 17. You're still at the same height. So every time you end up at a corner down here, right? And why do we care about that? We're looking for the 20/20th left turn. That's a multiple of 4, and it looks like it's going to go kind of in a cycle, 1, 2, 3, 4. 1, 2, 3, 4. And so he's going to be at a lower left corner when he completes this process. Okay, so let's go from the beginning. From here, I went down 2 and down 2 from the 20 as well. So we kind of wonder, is that always going to happen, and why is this happening? Let's kind of make sure of that before we move on. We don't want to get tricked. Okay, so from here, why would you go backwards 2? Mostly because you are going from here 1 this way and then 3 back. That's your net change in x. 1 to the right, 3 back is negative 2. What about your net change in y? You went up 2 and down 4. That's a net change of down 2. And this process is going to repeat. Here you're going to go 5 this way, 6 this way, 7 here, and 8 here. 5 to the right, 7 to the left. It really is subtracting 2. Up 6, down 8, it's subtracting 2. We've got it. It's an arithmetic series. And so we're just going to start. We're going to look for, since we went with 20/20th term, we're going to divide 20/20 by 4. That's 505. So this is the first term of the sequence is going to be negative 22, right? Because it's a sub 4, it's our first term, whereas 20/20 will be the 505th term. So we're going to start at negative 22, and we're going to add a sub n equals a sub 1 plus n minus 1 times d. We're using this formula if you can't tell. So we want a sub 505. That's going to equal the starting point of negative 22 plus 504 times the common difference of negative 2. This is going to give negative 1008. And then we're going to subtract 22 from that to get negative 1030. This is the x value of a sub 2020. It will be negative 1030. Quickly glance, there's only 2 answers that have that, so it's one of these 2. We have to repeat the process one more time with 18 being our first term. So we're going to have a sub 505 for this one equals first term of 18 plus n minus 1, which is going to be, again, 505 minus 1, times negative 2. You're again going to get negative 1008, but now you have a positive 18, so you're going to add it. It's going to get less negative, if you will, and end up at negative 990. And so we get answer choice B. Don't be afraid of problems like this. Just start making a diagram and reasoning about it, and you'll come to the answer after recognizing some kind of a pattern that will emerge in the problem. Now for the 2020 10B problem 14, which was also the 12B problem 11. As shown in the figure below, 6 semicircles lie in the interior of a regular hexagon with side length 2, so that the diameters of the semicircles coincide with the sides of the hexagon. What is the area of the shaded region? This is shaded, just pretend. Inside the hexagon but outside the semicircles. Probably the number one feature of a regular hexagon is that it's 6 equilateral triangles, at least in my opinion, number one feature. So we can take advantage of that. If we were to cut through here like this, and like this, and like this, you can see that each of the 6 center regions that are shaded in the original problem, each of these regions is equal. And we can just analyze one of them and multiply it by 6 to get the answer. So if I take an equilateral triangle and I construct a semicircle on the edge of it, then I want this region at the top that's inside the triangle but outside the semicircle. So how are we going to attack this? Again, with circles, you oftentimes want to add an advantageous radius somewhere. So if you just start from the center and you think about it, these are all 2, this will be 1 and 1. If I draw the radius here, this will be 1. And if I draw the radius here, this will be 1. And we know that this angle is 60 already, so this will be 60 as well because it's isosceles, and therefore this is 60. Then you know you have 2 60-degree equilateral triangles down here with side length 1. And what's this in the middle? Well, since this is 60 and this is 60, it's a 60-degree sector. So again, we're going to use S, which stands for side length, squared root 3 over 4 for the area of an equilateral triangle. The big equilateral triangle is got side length 2, so 2 squared over 4 will cancel. We're going to get root 3 minus, and now we have to subtract the parts we don't want. We can just do these two equilateral triangles, which are also s squared root 3 over 4, but s is just 1 this time. So it's going to be 1 root 3 over 4, or root 3 over 4, but there's 2 of them. So 2 times root 3 over 4 is root 3 over 2. Plus, we also have to add the sector in the middle. Now, sector area is simply the central angle over 360 times the area of the circle. So 60 over 360 is 1/6. Pi r squared, our radius of the sector is 1. We just don't need to worry about the radius now. Pi over 6 is that sector. Now, I'm going to subtract. This is like x minus a half or 1 minus a half. It's going to be root 3 over 2, because if you have 1 minus a half or root 3 minus root 3 over 2, you get root 3 over 2 minus pi over 6. And then we're simply, that's only one of the triangles. We've got 6. We're going to multiply. This gives 3 root 3, and the 6's cancel here also, minus pi. That is answer choice D. All right, now for the 2020 10B problem 15, the last problem of this set. Steve wrote the digits 1, 2, 3, 4, and 5 in order repeatedly from left to right, forming a list of 10,000 digits. Kid's got some serious time on his hands. Beginning 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2. He then erased every third digit from his list, that is the third, sixth, ninth, and so on, digits from the left. Then erased every fourth digit from the resulting list, that is the fourth, eighth, 12th digits from the left and what remained. And then erased every fifth digit from what remained at that point. What is the sum of the 3 digits that were in positions 2019, 2020, and 2021? The problem can seem like, how are we ever going to do this? That's a common feeling. You just need to try to think that, okay, they can't possibly want you to write all 10,000 digits. That means there must be a pattern that emerges if we just explore the problem. So let's get started doing that. Write out a good sampling of numbers, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Now, we're canceling every third digit. I stopped after the third set of 1, 2, 3, 4, 5. The reason I stopped there is that on the fourth set, since I'm canceling every 3 terms, let's see what happens. I cancel the third, and then the third, and then the third, and then the third, and then the third. So you'll notice we're at the start of a new cycle for the next step, meaning this goes 1, 2, cross out 3, 4, 5. So is this 1, 2, cross out 3, 4, 5. So we're going to repeat right after that. So this is after step 1. We are at 1, 2, 4, 5, 2, 3, 5, 1, 3, 4. Okay, then how many terms are there here? Well, there was 15 in the 3 sets up here, and we took out every third, which means you're going to lose 5. There should be 10 numbers here. Let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're good. You do little checks like that so that you don't find yourself at the end of the problem making a silly mistake. Okay, we do it again. 1, 2, 4, 5, 2, 3, 5, 1, 3, 4. All right, this is 10 numbers and this is 10 numbers. That's a total of 20. I went ahead and wrote 2 sets because in the next step, we are going to cancel every 4th number. And 20 is divisible by 4, so I know at the end of the second cycle of after step 1, I will be created a whole new cycle for step 2. So let's go. Every 4th digit now. So the 5 gets canceled. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Now let's write down what's left. We know we're starting a new set of this right here, and again the 5 will be canceled in that set. So we're going to get repeated process all the way out. We don't actually care where it ends either, because we're going to count from the left every time, so whatever, there's something over there. We don't care. All right, 1, 2, 4, 2, 3, 5, 3, 4, 1, 4, 5, 2, and 5, 1, 3. Okay, let's make sure we got it. 3, 6, 9, 12, 15 digits, which is exactly what we expect because there's 10 here and 10 here. We canceled out 5 of them because 20 divided by 4 is 5. And so we had 5 terms canceled. That leaves 15 remaining. And then we're going to start a new set of this variety, right, of this kind of sequence that repeats. So now we're going to cancel every 5th term. And because there's 15 here, I don't actually need another one. I'll start it so you can see what's going to happen, but I'm not going to keep writing it. Okay, I'm going to cancel every 5th. 1, 2, 3, 4, cancel a 3. 1, 2, 3, 4, cancel a 4. 1, 2, 3, 4, cancel a 3. You'll notice it's right back at the start of where we were. 1, 2, 4, 2, cancel a 3. Okay, so that's why we don't need to write this, because it's just going to repeat what we had here. We knew we could stop after one set because there was 15 in a set, and we're canceling every 5th digit, meaning that it will evenly go into the last number, therefore starting a new cycle. So let's write what we have now. We have 1, 2, 4, 2, 5, 3, 4, 1, 5, 2, 5, 1, and then it's going to repeat, right? 1, 2, 4, 2 again. So how many numbers are in our repeated portion? There's going to be 12 numbers here, okay? Why? Because we have 4, 4, and 4, yeah, whatever, you know it's 12. Okay, so we want the 2019th, 2020th, and 2021st. We need to find a number near 2020 that 12 goes into. So there's a number of ways you can do this. I think I'm just gonna, we need a number that 3 and 4 both go into. So if I look at 2016, I know 4 goes into this, 6, 7, 8, 9. Since 3 and 4 both go in, those are relatively prime, 12 will go into 2016. That means the 2017th number is this one right here, starting a new cycle after the end. 2016 will be the ending term. 2017 is this one right here. 2018 right here. 2019 is the 4. 2020 is the 2, and 2021 is the 5. We can simply add those up. 4 and 2 is 6, and 5 is 11. That's it.